Okay, welcome. I'm Dan. We've never met each other before. This is our usual Monday afternoon talk. Okay, so now I know who my true friends are. The ice cream truck will be outside after this talk for everyone who stayed. No. If I had that much foresight, maybe I should have done that, but I didn't. Okay, so talk number 2. What's neural and what's not in MRI? So, we're talking about MRI scan. You throw someone an MRI scan, they're kind of scared, they're kind of want to get out, and you collect some data. And you look at that data, you have that time series, you have, for that location, you have a bunch of time series goes up and down. This is 5 cycles of a block design task. What makes us think this is neural? So why do we think this is neural? I'll be a bit more interactive in this talk since it's the second one. Although I did say, okay, hour 2, so I guess I'm not going to be more interactive. If you look at this, you're seeing this. We know there's 5 cycles. We're seeing 5 cycles here. That's a good thing that might make us think that there's something here that's interesting. Look at this slide. This is, an ICA component from resting state run. What makes us think this is neural? What is it? It's what? Someone muttered something. So anyone who knows the field, this is sort of a classic default mode network. If you didn't know that, it's a bunch of contiguous blobs in gray matter. It looks kind of neat. It's symmetric. These things kind of make us think, oh, that's about neural. How about this one? What makes us think this one is neural? Okay, this is the second hour. This is what I get for being sick on Friday. This, believe it or not, this was published in a Glamour journal. Does anyone believe this? Well, it was published in Glamour, actually. So this is from I shouldn't be. So if anyone doesn't know, this is activation in the ventricles, which in past history was considered the seat of the soul. So maybe it is accurate, but most likely this is a motion artifact. And I should be a little bit not as harsh on the actual authors of this because they probably did not pick the slice to show, and it's possible that things aren't quite as bad in that paper as I thought. But push comes to shove. This looks like, when you're seeing things in the ventricles like that, it's nowhere else. It's a good chance you're having a motion issue or a head motion issue or something else. But this kind of comes down to the main point. With all these results, we don't know really that any fMRI results are neural. But for a well-designed and reported study, we can be reasonably confident. And what I'm going to try and go through in this talk is, where does this confidence come from? Both confidence for the field as a whole and confidence for an individual study. As a bit of a summary for the field as a whole, we know there's a plausible mechanism. The results match our understanding of brain function, and there are complementary studies with other measures. For an individual finding, our confidence comes from seeing that they used appropriate methodology, whether it's, I'll give some examples from task and rest, and I'll give a case study at the end. So starting out with plausible mechanism. Some of this might have been covered in previous slides here, but it all comes down to this idea that deoxyhemoglobin is an intrinsic MRI contrast agent. So if you take oxyhemoglobin in a test tube and you take an MRI image of it, it looks like a test tube, like a cross-section through a test tube. If you take deoxyhemoglobin and take an MRI of it, you essentially get all this distortion around the edge of the test tube. And if you look at in a brain with 100% O2 versus lower O2, you can see that the veins where that deoxyhemoglobin in are blacker when you're using a T2 star weighted image. And that's sort of the fundamental thing of saying we're confident this works because we know that this change in deoxyhemoglobin is going to change something we measure. And the plausibility goes back to this observation that when you have a stimulated versus rest state, you have a blood flow change, you have metabolism change, but what this is showing is the blood flow is actually changing. Oxygen to oxygen is kind of like the ratio of this, in this case, and it's showing that the blood flow is changing more than metabolism when you have a task. And what that means is you're with more blood coming in, you're actually getting more oxyhemoglobin in the tissue, and that's showing this neural activity-based effect that we see in BOLD. An interesting aside that I'm not sure Peter mentioned in his talk was the early studies of BOLD, they kind of assumed that more activity would mean more deoxyhemoglobin and the signal would go down. And then they started collecting data and they saw that more neural activity meant the signal went up. And after the fact, they found this, they sort of dug into this literature and said, oh, this is why, because it's actually the blood flow is overcoming the metabolism of oxygen. So there are many ways to visualize the neurovascular coupling. I've made this one, and I particularly like it because it's not confident. It shows that it shows what we do know, but also doesn't make it overly clean. So we know that when neural activity happens, you're going to have local field potentials, action potentials, ion transport. That's in some way it's going to cause vasodilation. That's your vessels expanding or contracting. It's also going to obviously metabolize oxygen. The oxygen metabolism means you get more you're going to have a change in your deoxyhemoglobin concentration. Vasodilation means your vessels are going to get bigger and more blood is going to flow in. That blood flow, more blood flowing in is also going to affect how much oxygen you get. And so this blood flow plus your blood volume plus your deoxyhemoglobin concentration are what you get at BOLD MRI. If you're looking just at your blood flow, this is this arterial spin labeling or flow MRI. And if you're primarily localized towards blood volume in vaso MRI. So this kind of shows the link between common MRI measures and this general network of neurovascular coupling. And again, I made this picture messy because I think it's, I don't want to make it seem like this is a precision. But if you're talking about the MRI BOLD, of course, this is just another way of showing it. So you have your neural activity. When neural activity increases, you get some oxygen metabolism increases. With a bit of a delay, you get some cerebral blood flow increases, and some volume increases. At some point, your deoxyhemoglobin and your BOLD are going to go from possibly there might be a little bit of a dip. This is slightly controversial, depending on the situation. Eventually, you're going to get increased deoxyhemoglobin, and increased BOLD. Okay, flip that. You're going to end up with, and BOLD, and then it returns to a baseline. Now, I'll focus that this shows what happens, not why it happens. So why is this happening? There's several ways to think about this. One is going back to that initial picture of what uses neural activity, and you can just say, whatever uses more neural activity is more driving the BOLD effect. So if you look at where the energy goes in the cerebral cortex, most of it is in this area of synaptic transition. Action potentials are just a small part of it. Resting potentials are a part of it. And sort of this housekeeping functionality, which is like, getting membranes back to their baseline state is a large part of it. So a lot of talk is on the synaptic, but this varies by brain areas. So if you go to the cerebellum as opposed to the cerebrum, you're seeing a lot more happening in that resting potential and housekeeping. One thing to keep in mind about this is we know that even though this should drive it, there isn't a one-to-one correlation between what's using your energy and what causes vasodilation in this whole network of stuff that causes the BOLD signal. And what's cool is over the years, we actually do know quite a lot about how neurovascular coupling works now. And it's not directly driven by oxygen or energy needs. So, if it's specific things, so like looking at this pathway, so this is your smooth muscle. If you're having, nitrous oxide concentration is going to affect it. Calcium ions concentrations are gonna affect it, and there's all this stuff. So, it's not just energy and specific, it's specific pathways and specific ions that are going to cause vasodilation and vasoconstriction. So it is quite an advanced model. But the other thing to keep in mind is there's a lot we don't know. So I just highlighted every question mark in this plot. And you can see that, there is so much detail, but there's still quite a bit that we're not quite sure of. And here's just one example of that neurovascular coupling complexity. There's a large argument in the field of when we do bold, we see the signal drops below baseline, and there's arguments whether that's because the veins aren't constricting fast enough or there's extra metabolism. So in this specific study, they did bold cerebral blood flow and cerebral volume measurements, and what they showed was bold dropped below baseline, but once the stimulus came off here, the flow and volume returned to baseline pretty quickly. And what that says is whatever's keeping bold below baseline there was most likely a more metabolism issue than a sort of a vessel diameter, just a balloon type issue. But there are other studies that have shown the exact opposite. So even something as simple of why does the signal go below baseline after stimulation is kind of up in the air. But then we get the question, so why do we believe this is neural at all? And there's a bit of a circularity to this, but at some point it becomes part of the evidence, which is the results match our understanding of brain function. So if you look at sort of how the field progressed over time, at the very beginning, people weren't studying emotion. They were studying primary sensory. So you're showing people a flashing light. Because if you're not seeing a response to a flashing light, what you're not studying anything more complex. And once there was enough confidence that things like flashing light, they were doing basic motion. The early tasks, you were getting a bit of cognition. And by the time we got to 2001, when sort of like the fundamentals were shown that the method works, then you're sort of seeing a bit between like basic cognition, higher order cognition, and stuff. Just an example of one of these earlier studies, all the way back in 1994 was the first retinotopy study. And what's amazing, what's fun about retinotopy is we have known about retinotopy since post-World War I. The original studies of retinotopy were based on traumatic brain injuries to the back of the visual cortex because of lousy helmets for soldiers. The Allied helmets didn't cover the back of the heads. They had a lot of visual cortex injuries. And some neurologists mapped that out quite well. So we've known about retinotopy since way back then. If no one knows what retinotopy is, it's the basic idea that what you see in like the top right visual field appears in your lower back left visual cortex, and what you see, in your top left visual field appears in your lower back right visual cortex. So it's the idea that your the visual space has a one-to-one mapping onto your visual cortex. So we've known about this at the time, we've known about it for close to a century, and it was robustly, supported, but we'd never seen non-invasively in humans. And this study came with a very elegant design. It just showed flashing checkerboards in hemifields that moved around and to different locations, and it was able to show that depending on where the hemifield appeared, you would see the activation sort of in the retinotopically appropriate area. So when you're seeing an fMRI result that's actually quite spatially specific, that maps really closely onto really long findings, that sort of built up some of the field's confidence that there might be something here. And you can take this to the extreme where the study by Jonathan Palomini, they said, we know that if I show someone an image that looks like this, we should see an M on their visual cortex. So our confidence in retinotopy is so high that you could essentially map an M activation onto the visual cortex just because. This was part of a study where they wanted to show a high spatial specificity image, and if they could show any image, they might as well show an M for MGH. They're the place where they did the research. Other early studies that sort of built confidence in the field is the response. For a long time we knew that you have a stimulus that you stimulate more rapidly, it's going to cause more neural activity, and again, these early sensory studies were showing that it's scaled with responsiveness. You also had very early studies showing possible clinical applications that also match the invasive literature. So there's an unpleasant test called the WADA test, which if someone is undergoing neurosurgery, you essentially inject a chemical to temporarily knock out half their cortex. And the purpose of this is you don't want to damage speech, and you want to know what side of the brain speech is on. So you, particularly in patients that are left-handed, speech can be in either hemisphere. So you knock out a hemisphere, and you could say, did it damage their speech? And if it didn't, then you know that the hemisphere you hit isn't their language hemisphere, and it's safe to be a bit more aggressive in surgery there. But that's not the most pleasant test. So from really early in the history of fMRI, people are trying to do better. And here was an early study showing that language does have a hemispheric effect in patients. For resting connectivity, one of the early studies that gave the big issue in resting connectivity is kind of, the argument's kind of in some ways gone away, is you're looking at correlations between the area. Anything that correlates is going to make your signal. So you have the same vascular tree. Your vasculature is pretty much symmetric. So if something's happening in your vasculature in the left hemisphere, it's going to happen the same way in the right hemisphere. So maybe all of resting connectivity is just correlations between vascular hemispheres, and that's why it's so symmetric. So here's a study that's pretty early in the world of resting connectivity, where they took patients who did not have a corpus callosum. So the corpus callosum is the main bundle of neural fibers that communicates between left and right hemisphere. And what they showed is if people listen to a task, both their auditory cortices are active, but if you try to do a correlation from one auditory cortex, it's not correlated with the other. If you do this in healthy volunteers, it is correlated between the two. So it's showing, this is an early fundamental study that showed that there are correlations between the two. And I should say this, in some ways, like the meat of this argument has gone away. But at the same point, all the arguments about how to remove noise is still in the same thing, because we know vasculature and other things are causing some of the signal, and we want to remove enough of the signal we don't want and keep the stuff we do. So this argument hasn't completely gone away, but it gave us this confidence that there is something there of interest underneath. The other thing to keep in mind is, the other thing that gave us confidence in fMRI is complementary modalities. So I'd say when I was sort of just getting into this field, this is the study that sort of finally got the attention of neurophysiologists because it used their tools. And it was a methodological tour de force, where they essentially collected direct electrical physiology using electrode in an MRI scanner in a primate, and they're able to get essentially simultaneous MRI and local field potentials from the electrode. And what they showed is, as the contrast of the image increased, you had both your electrophysiological measures and your bold signal increase in pattern, in sync. If you plotted your local field potentials or your electrophysiological measures over bold, you get a nice straight line. So this was showing that, in a specific animal, this is not like comparing, past literature to this, but in this animal, your electrical measures matched up directly with your bold measures. And this, I think, took sort of the field of the respective bold as a field to another level. And I'm going to talk about some of the other complementary methods, but just to do a summary, when we're talking about how this neurovascular coupling is studied and how this, what we're looking at in general, there's humans, non-human primates, rodents. Some of the studies are, something to keep in mind if you're reading this literature is some of the animals are awake, asleep, task, rest, and with and without anesthesia. the results vary a lot with anesthesia, so it's something to be aware of. The imaging tools are growing every year, which is just wonderful to see. So probably the newest ones are these 2-photon images and just these super high resolution cortical sheet measurements. And with things like calcium imaging, you can sort of see, you can almost get like a neural equivalent of bold in animals. Unfortunately, it's very invasive, so it's something that's limited to animals, but it does greatly inform what we do in humans. Here's just one early example of what an optical measure would look like. What you could see is we get total hemoglobin, we get oxyhemoglobin, and deoxyhemoglobin. This is sort of a sheet of the cortex with the vessels. And with a given stimulation, everything kind of starts flat. You're seeing your total and your oxyhemoglobin go up first. A little bit later, your deoxyhemoglobin peaks mostly in the vessels, and then they return to baseline. So things like this are also building up our support for why the stuff we measure. Essentially, it's complementary to what we're seeing in bold. Similarly, there's a lot better EEG results out there nowadays, but I wanted to focus on this, which was one of the earlier ones, that just shows, there's relationships between the EEG, which is sort of a electrical measure on the surface of the cortex of the head, versus fMRI, and you can see that some areas it was positive or negative correlating. Although I'll note this EEG-fMRI relationship isn't quite simple, because a lot of people say like, oh, EEG is a gold standard, but you can actually say EEG also, this sort of baseline signal also correlates with your breathing depth. So breathing depth you normally think of as an artifact if you heard my last talk, but when people breathe deeper, they might be relaxing more, they might be falling asleep. So it actually is, it's also a neural measure, so that makes things a little bit extra tricky. This study I kind of like because it tells a two-way story. So particularly with resting state connectivity, we've been looking at these sort of really long, slow frequency changes over time. So we're looking at a 10-minute scan, and we're seeing like, on the order of seconds or minutes, the correlations between brain areas increase and decrease with time. And this study took electrodes in different areas of the primate brain and showed that they also had that same effect with similarity in their connectivity patterns at both high and low frequencies. And some of the bigger connections actually are at these low frequencies. So what I think about this study, what I like about this study particularly, in addition to sort of giving a more direct neural basis to our fMRI findings, is it's I think one of the early examples of research going both ways. So for the first decade or so of fMRI, all the electrophysiologists were looking at fMRI saying, you're not measuring neurons, we don't care. And then you hit this point where it's like, okay, maybe this is a decent indirect measure of neurons, but it's not affecting their research. Then resting state came across, we're looking at these really slow frequency fluctuations. Mostly up until that point, a lot of our electrophysiology was all about speed. It's, you're doing a stimulus, you're seeing your response is over in the order of, tens or hundreds of milliseconds at most. The idea that you're looking at a slow electrical frequency fluctuation over the period of tens of seconds really wasn't a central area of research. Then fMRI comes along and shows that there are these interesting slow things happening. And then various people in the electrophysiology world started looking at these slow frequencies. So now the fact that there are these slow fluctuations is sort of taken for granted, but I think it's one area where fMRI actually drove neuroscience research in a new direction. So that's sort of the first half of this talk, a little bit more than half, talking about why we believe that there's a specific, why the field believes that fMRI is worth something. The second is now, why do we believe a specific study represents neural activity? So this is back to my introductory slide. And we're going back to this original one. So how do we know this is neural? I assume the room is still as enthusiastic in hour 2, so I won't do a long pause for questions. Although, seriously, if anyone has a question or anyone wants to comment, feel free to interrupt. If not, thank you for hanging out with me for an hour and a half to 2 hours. So I said that we see this nice big response here. And this is sort of that same response from this location. We see the same response from that location, that location, that location, that location. So this is sort of ventricle, seeing the same response. So the question is, how do we know this is neural? And the answer in this case is it's not. The task I was doing here was a breath hold task, which is causing a global blood flow response across the whole brain, which might have some neural input to it, but primarily this is just vasculature. This isn't going to be driven by a neural effect. So this is sort of my first point of showing that just because something at a surface level looks neural doesn't necessarily mean it does. How do we know this one is neural from the beginning? It actually isn't also. This was from a study that was trying to regress out noise from data sets, and that map that looks like default mode was actually the residual of the residuals, still showing the same effect. And there are reasons that appears there. That's not as bad as it looks, but it shows that things aren't as clean a story as they could be. So when we're talking about isolated neural signal, this kind of fits into my previous talk too, where you have, let's say you have two signals that are perfectly correlated, and one signal that is quite different. So these have high correlations, this is low correlation. We're going to add scanner-based noise, which is essentially random. We're going to add cardiac and respiration noise. And for these two, we're going to add a spike from head motion at some point. What we get now is, instead of a perfect correlation, this is a slightly worse correlation, and this is a lot better correlation. So when we're talking about getting confidence that something is neural, it's figuring out what happens between our true time series and what we actually can measure. So the challenge is we got respiration and cardiac. I think I drove that home a lot in the last talk. There's head motion. I think I've mentioned that a bit too. And understanding the effects of your data processing choices and data collection choices. Respiration can bias fMRI results. Here is another study that shows, sorry, I didn't look at this one beforehand. In this study, there's doing a breath hold during the task, and it's actually affecting what areas do and do not appear during this task. You also have connectivity differences based on head motion. So here is, they had a single study, and they divided the study into different groups based, sorted by how much they moved their head. With group 1 had the least head motion, and group 10 had the most head motion. So all during the same resting state scan. And you can see that based on head motion, you're getting quite different results. And the big thing here, of course, is here was just sort of, a natural example. But if it turned out that you had if this was actually a population study, and one population had more or less head motion, that could be a pretty significant issue. Spatial resolution also matters. So you're going to get, here's something where you're looking at, you can have a very fine effect at a 7 Tesla image, but if you smooth it, you get sort of a much more robust effect, but you lose some of that specificity that was lost. Data processing also matters. There's a common pre-processing step, I think it's still common, unfortunately, which will always result in networks getting anti-correlated. So what this study was showing was that, so a lot of resting state connectivity studies removed what's called the global signal. So it's the average of the whole brain time series. And the reason they did that is they assumed that anything that was correlated, all across the brain couldn't be something interesting, so they should remove it. And that's 100% true. The trouble comes down to a basic mathematical principle. If you take a bunch of time series and you remove the average of all those time series, and then you correlate them to each other, you will always, always, always change no matter what those original time series are, you're going to change the relationships to each other. The most extreme example you can think of is take two time series that are completely random noise. Average them together, and remove that average from both of them. They will become perfectly anti-correlated. So that's sort of the most extreme example. But the same principle holds that when you're removing that average, you're going to sort of be amplifying this anti-correlation. So there are cases where this still might be a good thing to do, but if you really care about what your correlation values are, this is going to always distort it. And I should say that there are anti-correlated networks in the brain. It's not like anything anti-correlated is an artifact. But what it's saying is you're not going to be able to actually understand what is or isn't anti-correlated if you do such a brute force pre-processing step. Another thing to bring up is modeling your response shapes can vary. So some of my early work was showing that if you just look at the hemodynamic response, so you have a short stimulus, this is the response shape. If you take 20 people, each of them has a different response shape in primary motor cortex. If you assume those are consistent, and you say how much does that affect your results, what you're seeing is if you're using that model precisely, then your estimate's going to be perfect. But if you sort of add a temporal lag, so you say, my true response peaks here, but my model peaks there, you're going to see a shift. And there are ways to correct for this, sort of adding first derivatives into your model and other things. But if you're not aware of it and how they interact, you're going to end up with a bit of trouble. Also, in general, the modeling of neural event, the timing order of neural events is really dicey. So there's a lot of people trying to talk about causality in various forms in fMRI, where you're trying to say in my fMRI time series, the event in visual cortex happens before the event in motor cortex or other areas. And the trouble with this is most of these are sort of working from a mathematical perspective, not a physiological perspective. And the truth is, different areas of the brain, when the neural event happens at the exact same time, are going to have different bold responses. So that's the shape response. And I looked at one method that has some popularity called dynamic causal modeling. And I showed that, can you predict the order of, does the event happen in node 1 versus node 2, or node 2 versus node 1? And what I showed is, if they're identical, it's not going to really show any effect. So sort of crossing this line would mean it's significant. If I shift the peak 1 second direction, which could actually be a neural effect or could not, it may or may not be neural in origin, you're going to shift it. But then I did things like I played with the undershoot. So the undershoot is, two hemodynamic responses that look the same, except one goes further down than the other. So I didn't play with the peak at all, and I used this model, and I showed a timing effect purely because there was a bigger undershoot. And this is just one example where if you're not really modeling and understanding what the true range of variability is, you're going to sort of get caught into issues that make causality and modeling timing really, really challenging or impossible. I actually presented this in the last talk, so I'm not going to present it again, which is that if you can have population differences too to be aware of. You're going to get a bunch of talks on multi-echo later in the series. But one thing this is sort of a nice, just a preface to it. The basic idea is if you collect data at different echo times, your response is going to increase, your bold response is going to increase till you get to an optimal echo and then decrease again. And what's nice about this is you can, if you make a model which is essentially your echo time versus signal change, you can sort components by that model, and you can say this is a component that the signal is changing in the way we expect bold to change across echoes, and this is a component that doesn't change in the way we expect bold to change across echoes. And if you look at what those components are, one looks bold-like, one looks like a motion artifact. You can see by the high signal on the edges there. And here's just another example of that multi-echo method. You're going to get a lot of talks later in the series on this, so I don't have to go into too much depth. But here's one time series. Here are components that were kept. Here are removed. And you see the kept components look things like our block design task. And the removed components look like things like cardiac artifact, signal drift, and respiratory artifact. Just to finish up, one thing to keep in mind about what is neural and what is not is, a lot of bold sort of fMRI focus on where our blobs of activity are. But this study was a bit unique in that instead of collecting 1 session of data, we collected 9 hours of MRI data across 9 sessions of the same 5-minute flash and checkerboard task. The volunteers were amazing. I can't thank them enough. And what was shown is more data equals more activation. So as we added in more and more of those, so it was 100 runs, 5 minutes each, and as we used more and more runs, more and more of the brain got active, until essentially the entire gray matter cortex was active by the time we were using all the data. So when we're talking about blobs and what's active and what's not, it's also limited by how much data you collect. So that's always a reason to think about collecting more data if you can. But what's extra interesting about the study is it opened up this whole new question of, so what's happening? And this was a flash and checkerboard, so this was sort of our response in that main flash and checkerboard area, which looks like a classic hemodynamic response. But you go around the whole cortex, there's negative responses, there's responses with small transient peaks, there are responses that are almost all the transient peaks, there's all this stuff going on. And there was a follow-up paper to this in cerebral cortex a couple of years later that delved into this a bit more. But it sort of opened up like the way we think about BOLD and what we think about hemodynamic responses might still be a whole lot more complex than what we're thinking about now. And there are non-neural things that can explain these findings. I could do call and response. I can ask for questions here, but I think everyone's ready for the answers. There could be luck. There can be specific analysis decisions. There could be head motion, voxel size, or global blood flow dynamics. So what did we do to account, to try and remove these from the possibilities in this specific study? For luck, replication is the best counter for luck. So we did this study in 3 volunteers. They all showed the same effect. We did a follow-up study with 3 more volunteers. They showed the same effect. We have another follow-up study in the works, and that's been collected with 2 more volunteers showing the same effect. So that reduces the chance that this is luck. For the specific analysis decisions, we did a lot of variance in the analysis, changing how we did alignment, how we did motion, how we changed the amount of smoothing, how we fit the model. The finding is consistent. So it wasn't the bias of like a specific analysis decision. For head motion, there's sort of characteristic things we'd expect to see for head motion of like how the artifacts appear, and it doesn't look like that. So again, this is sort of leaning on expertise for that one. And for global blood flow dynamics or blood steal, the idea there is that if you have a lot of activity in one area, then the blood that goes there has to be coming from somewhere else, so it's going to affect other distal things. But the trouble is the spatial variation of those response shapes doesn't match what we'd expect blood steal to look like. So it's not like the signal goes up in one region and down in others. There's these transients, there's other stuff. And it actually changed, and the amount of magnitude actually changed when we changed tasks in the follow-up study. And so this is sort of that follow-up study where you're seeing that, if you're doing a full flashing checkerboard versus a hemi-field versus no task, it does change. So there is a neural component to how much is active. So going back to that original idea, was it luck? No. Did we make analysis decisions that caused that? That was very unlikely. Head motion, unlikely. I don't think it was the voxel size. I didn't focus on that because the follow-up study also used much smaller voxels. As a blood factor, it might be a factor, but it doesn't really explain all the results. So that's just sort of one case study example of how we can look at a specific study and decide, how do we have confidence that it is neural. In summary, fMRI helps us understand the brain. Yay. Even though it might measure an injector signal, it can be quite specific. There are many ways to confuse artifacts with neural signals if you're not careful. And to best do this, you really got to think about your choices with data collection and analysis, and look carefully at your data. And that's about it. I guess I went much faster on that one, which is probably good for everyone. Okay, any questions? Yeah.
Yeah, I have a question. So fMRI gets like a correlation with then do you ever compare it to like a more like direct measure of blood flow studies?
Yes. So the question is MRI compared to other more direct measures? So there are some MRI PET studies. There are some studies that do sequentially MRI and PET. There are actually now MRI PET scanners that are together. So there's a few studies going out doing that right now. But more generally, there's a lot of studies that use, for simultaneous stuff, there's MRI EEG. And MRI electrophysiology is actually significantly more common now. That shows direct measurement. And push comes to shove, there's a lot of relationship. I think the bigger issue in general is I think you're going to see more changes in fMRI than you might see in any specific other measure. So like electrophysiology might show something in LFP, and BOLD will also show that, but it might also show something relating to a breathing artifact. So that's kind of the trick. So I think we have really high confidence that if there's a large enough local field potential change with electrodes, we're going to see that in BOLD. The question is, you can't sort of say the opposite and say, we see a large change in BOLD, therefore it must be local field potentials. So it's kind of one directional, and that's where sort of a lot of this other stuff fits in. Okay. Well, thank you all for staying here for this.